But today my talk, I guess, is more like apply, like a more engineer. How can we use a machine learning or machine learning models to apply, for example, to address complex energy materials. So today I'm going to talk about give an overview of our research related to the modeling of complex energy materials with machine learning, which is use our open and free source code, the Atomic Energy Network or AENet. And once we develop our tools and models and database, we share with the scientific communities. As I already mentioned that I myself, I'm a computational material scientist. So actually my work mainly looking at is depending on the accuracy that we are interested in, is starting from the density functional theories or DFT or interatomic potentials, or even much larger scales if we need it to describe the accuracy, depending on the research questions. But in this talk, we will focus on this type or length and also the accuracies by using machine learning models to address and to train the accuracies of a DFT that can then later use in molecular dynamic simulations. As you know that many, for example, many processes of electrochemical interfaces is really very complex systems. It's really challenging for the simulations. So if we would find energy models or models that can describe, for example, necessarily to describe the reactive, for example, bond breaking or bond forming, or molecular in gaseous, liquid, solids, and interface, or sometimes non-ideal surface with various different types of defects, and also include like the solvent effects or electric fields. Like the cartoons that I draw here, you can see that there are so many things happening at the surface and at the interface, and also really complex reactions. So there is no realistic and accurate DFT or first principle methods can describe such a complex and large scale like this. So that's why I think machine learning models that we develop could also maybe help to looking at such a complex system like this. And not only this, for example, we're also interested in energy material like batteries. Batteries are really complex. It's also very challenging. Use just only accurate DFT methods. For example, you can look at the two different experimental images here that I just show as just example. On the left-hand side, this is the interface of solid-state batteries. You can see this is the cathode. This is the order lithium cobalt oxides, and near interface, this is the disorder of lithium cobalt oxides. And the electrolyte, this is the LiPo and also the anode here. And another side, this is a silicon anode. You can see that after battery cycling, you can see amorphous structures. So the most important part to understand and to address for modeling or for computational material scientists like me. So we are interested in such nano-sized particles in these domains, right? And also interfaces and also amorphous phases. That's why, for example, we try to combine atomistic simulations and machine learning together to address more realistic systems, especially in this case, I pointed to like the interfaces. So before we go and to look at some examples of those complex energy materials, I would like to briefly discuss the methods that we use, but really very high levels. So machine learning potentials for complex materials. So we use, for example, find accurate model to represent potential energy surface. Or in the next few slides, I will use the PES from very accurate energy methods. For example, quantum chemistry or quantum mechanic methods. So first, we generate really large database. And then we use a machine learning model to interpolate and construct a continuous, efficient, and accurate machine learning potentials. And then we apply the accurate energies and, for example, also forces in large length and also long time scales in MD and MC simulations. So our methods, we use artificial neural network for interpolations, because it is really can represent the reference data really highly very accurate and can handle really very large database. And the input, we only need atomic positions, and we can really construct a reactive and also full dimensional. but it takes also a bit of effort to construct realistic machine learning models or neural potentials to use for your own applications. So actually using neural potential is the idea of to use NN to represent potential energy surface. This is not news. Like you can see here, I just list a few examples that really related already since 1995. Dorian already showed that the first potential energy surface can use it, for example, like the nickel 111 and also carbon monoxide. And also 2004, Chebyshev group also show some models that can describe really complicated palladium 100, hydrogen molecules, and also potassium here. But this is really specific or really like just the system that is only tells for such a system of specific system. But 2007, Baylor and Polynomials, that the first time that apply high-dimensional neural potentials to describe any number of atoms and also many different phases and describe a single chemical species, silicons. And then once I joined the Baylor group together with Professor Baylor, we extended the methods for multi-component system and also include electrostatics interactions, and we describe zinc oxide. And then when I joined the SETA group, because we work on really complex energy material, for example, batteries, it contains really many different chemical species. So we extend the methods, and then I will also demonstrate in the minute. And also 2017, our Reutberg group show really large data set that can really describe for many different chemical species. Like you can see here, since 2011, neural potentials have become more and more popular. The number of publications per year is growing very fast. Like I just showed here, just some quick example in October. You can see really very fast. But as you can see, that still already many models, but not many really potentials can reuse. This means in the field, I mean the subject still really need how to say, like, to make it easy also to use and also share with many other scientists, right? So actually, there are many aspects that we can describe, but only one aspect that I would like to point this out here, and also one of the part that I also contribute to the development. For example, you know that descriptors to describe your input data or your input structure is very important. So descriptor has to follow the invariance, for example, of the energy here. You can see the properties of the atomic energies, the total energies of structures. For example, sigma here is the sum of atomic energies, and the atomic energies have to follow the physical invariance of the total energies. The atomic energies have to be also invariant with respect to exchange of equivalent atoms and with respect to translation or rotation of the structures. More detail you could look at in these two publications. Additionally, a descriptor needs also to have constant length, and each NN has to be one specific number of input nodes, for example. Therefore, the length of the atomic structure descriptor has to be constant. The size of the descriptor also has to be independent of number of atoms and chemical species of the structures. So this is the wish list of the descriptor of local atomic environments that we try to address and to have it, to make it easy also to use for realistic applications, right? So this is a few points that we made. For example, the descriptor should like no menu parameter, no, how to say, it should be automatically described and easy to use, and also systematically refinable, and also should be really very efficient when we increase, for example, many different chemical species, as I already showed before. I would like to briefly discuss that the descriptor that we discussed here in 2017 in PRB. For example, here we also develop filters based on the symmetry function that described already from Baylor polynomial descriptor by described by using radial distribution functions or RDF and combined with the angular distribution functions or ADF here. But this is A and C that I have it here. This is the descriptor to describe atomic structures. you can see that we introduce an invariant already, it's RDF and ADF, but we use the Chebyshev to expand the coefficients, like the order here, like you can see the alpha, and then combine with many different cut, like you can see here. This is the central atom, and this is the atom in the R cut. And this is just to describe atomic structures. And if you have many chemical species, so we also introduce another set of the descriptors by introduce the weight of atomic types. For example, here, WTJ. So this means if you have one chemical species, we introduce 0 as a number to second set of your descriptor. If you have 2 chemical species, you introduce like a -1 and +1 to describe this is 2 different types of chemical species. If you have 5 chemical species, we have -2, -1, 0, +1, and +2, for example. This is the weight type that we use it to classify different type of chemical species. Maybe the cartoon is look a bit not easy to understand. I also show here just a quick equations to describe how the Chebyshev descriptor or the expansions of the coefficients that we use to describe our atomic structures, and also another set to describe many different type of chemical species by introduce the weight type of chemical species here. So this is how we combine 2 types of the descriptor to describe our atomic structures and atomic chemical species to use it as input for our neural potentials. This is just a benchmark to describe 2 types of structures that we have in the database. So the first one in the middle here, this is the lithium metal oxides that we have. You can see that many different types of chemical species that we did benchmark. In the x-axis, this is the descriptor dimensions, and the y-axis is to show the accuracies of our neural predictions compared to the DFT reference data. You can see that many different types of structure and chemical species, it really get very low root mean square errors, like around 3 millieV per atom. And the same also for molecular system that we have. This is also very accurate. So this means our Chebyshev polynomial descriptor really can work for complex system. We also introduced another type of method can use it, because we know that forces also very important to use or include in the fitting or neural potentials training. So we introduced a new method. This is including atomic forces via Taylor expansions. I can show, okay, maybe I forgot to have it as a simple slide that I can explain. Okay, I have it here. So the idea is that, for example, here, we introduce, this is to show if we fit data, only the energy training, the sample, this is the reference data, this is in blue circle here, the bond length, and this is the energies. And then we use neural network fittings. You can see that sometimes it looks very good with the training, but it's not really, not always give the right prediction of atomic structures or the energies. But then we introduce the method. This is include forces to approximate the energies via Taylor expansions by introduce such a small atomic displacement. It's also depending on the materials or chemical species, can be like a liquid or solid. These small displacements of that we introduce also can be slightly different. So now looking at on the right figures, so this is the same reference data, and then we introduce the Taylor expansions. You can see we introduce a few more data points, and then we fit neural potentials. So now we can see more accurate neural potential that predict the right atomic structures and also accurate energies, like you can see here. So as I already mentioned before, it's really depending on the system. This is just to show example of the 6 water molecules that we have. The x-axis is the maximum random atomic displacements that we introduce to introduce more energies of the structure that we introduce. For example, like a plus x and minus x of each atoms. And this is to show the relative mean absolute errors of atomic forces. You can see that for this data set, the distance that we introduced is around 0.01, show the best performance of predicted forces from our example or our benchmark here. And we also check that if we compare just by looking at like directly including all forces in the training set, we can see that it is very accurate in the black curve here on the figure B here. But the time that we use it take longer, like 8 times of the more computers than just using the introduced Taylor expansion methods. You can see that the blue one, this is the accuracies of the forces that we have, the errors, is also quite okay or improving just then without using the forces. So this is working okay if we work on molecular system, but in realistics, my work mainly is based on the condensed period structures. Direct force training is really very time consuming. So we also test and check. So using our direct force training for this complicated 5 chemical species of the lithium cathode here that we have. So it really doesn't work. But we use then our methods by including the force information that estimate from Taylor expansion is also work really well. So I will show you one examples that we just used. This is just 800 DFT reference calculations. But again, this potential is not really ready used, not general, but this is just to show as the benchmark. And we use just 800 structures and then train only energy only. You can see that our MD1 is kind of like not really easy to stables or some kind of like not really convert easily. But with the we also run many of course many models. You can see that even in the red also really explode so early. But includes the neural network include the force information from Taylor expansions, make our MD simulations of these models. It's a really long time simulation and stable in MD simulation. So this is also help us as a practical, right? If we really have more data, but we don't know how large of the data set that we have, we just introduce our Taylor expansion methods. It's also help to generate and construct a good or stable neural potentials. This is the diagram or just how to construct a potential energy training in practice. So if you are interested in, this is the diagram that we also show in our paper here, including the share, the database, and also how to use everything in Git. You can follow this GitHub link. But just to save time, I also would like to show you that our init code, this is open and free that you can really try and test. We also implemented interfaces with many others software that is ready used, for example, with ASE code, with LAMP and Tinker, and also our own genetic algorithms that you can use for many different, based on your own applications. So init is also really widely compatible with many high-performance computing architecture and systems together with the main developer, Professor Urban. So we already try and test and use from many different HPCs, for example, from the US DOE, NERNS on SSF axis, and also DOE from BNL computer clusters, also Columbia computers, and also now in the Netherlands. So we also got a location from NWO Serve Dutch. And not only this, we also don't know other type of computers, because also we also collaborate with many other scientists here. Like I just showed, actually many more, but this is a few scientists that's still active and also join us to develop init. And this is just a quick show, like our init code is really highly parallel. For example, in this benchmark, we just do 1 million atoms of water, and it only takes 15 seconds in like a 10 MD steps that we run in the 96 CPU cores in the supercomputers, like you can see here. It's really nicely scaling parallel here. It's only 20% loss if you use even many more nodes. But in realistic, in your own simulation, you don't have really 1 million atoms, maybe 10K atoms, for example. So you can really run long-time simulations, or you really can extensive samplings for your own applications.
You have 5 more minutes.
Okay, great. I think I'm more or less done to show of the methods, but I can briefly show how we apply and use the method for the application really. But I will just look at like how, just not talk about science, but just want to show that how our model can really address complex energy materials. So the first model is this copper gold nanoalloys, which is the good catalyst for CO2 reductions. And the quick system that I will show, like copper serial oxides, this is a good catalyst for CO oxidation. Let's take a look at, so here, this is copper gold nanoalloy. It's really complicated. Like you can see that if you use only pure copper here, it's oxidized in the reactions, it's very fast, and also it stay very long. Sorry, very short in the reactor. But if we mix copper gold, it's stay really long in the reaction. But how can we really help our experimental collaborators to find where copper and gold really rearrange? So we also use our neural potentials to help to find atomic structures. For example, this is the first example that we generate, and we find many different types of nano cluster size, and also rearrange. We apply ANN and Monte Carlo simulations in annealings, and we see that gold like to stay on the surface, and then copper, orange like stay in a mixture. This is in vacuum. And you can see that if we do the FT calculations in 147 atoms, it takes like maybe 3 hours, even with 16 cores. But with efficient and accurate neural potential, we just use 1 second per core to predict one energies. But in realistic, like I just showed the experimental cluster size, 4,000 of atoms, using just accurate DFT is very difficult to find such a models or these compositions. But with our neural potentials, it's like 1 minute, right? And not only this, our models can also use to run MD simulation to find many different compositions, and also to really looking at melting points. So more details, maybe we can go to the discussion room to check and discuss in detail of the work. But just I want to show that how can we use our neural potentials to many different applications. And not only in vacuum, we also can extend our dataset with like more solutions and also interface that you can see here. So with our efficient and potentials, we can really do a lot of kind of like more realistic models. And another example quickly, we also can help our collaborators find where, for example, the orange copper sit in the atomic structures, which is because of in the images from the TM. In the experiment, they only see like black and gray. They don't know where a little atom sits in the structure. So with our neural potentials and Monte Carlo simulation, we help our experimental collaborator find where really copper can sit in the structures, for example. And also for batteries materials, like after battery cycling, so atomic structure really become amorphous. There are so many phases, many different compositions. With efficient and accurate neural potentials, we can really help to find many different composition and phases, and also the structures. And not only that, also help to find the accurate, like the diffusion paths, which it can occur. There are so many different possibilities that, for example, like lithium can go in many different types of the channels, and in the battery cycling, the atomic structure of lithium also like extractions or insertion. So there are really many different composition. Yeah. And yeah, I just want to show that. Yeah, I think at the end, I would like to show that using our accurate and efficient machine learning models can really do a lot of application, and also more realistic. Maybe I will just jump to the conclusion, and also like to thank the work that my students or my people from the past, because I just joined Utrecht. So the work that I just talk is based on the past few years. This is a team from Colombia, and also the support from the Department of Energies, and also computationals from the NSF Exceeds, also CFN. And thank you very much for your attention. I'm happy to take questions.